Hello, everyone. This is Nuclear Chemistry Made Simple with Ms. Rodriguez, and today we're going over everything you need to know about the nuclear chemistry unit in high school chemistry. Today we'll be going over three things, and that's the different types of nuclear reactions, the difference between fusion and fission reactions, and how to write nuclear equations. But first, let's learn a little bit about nuclear history. So everything with nuclear chemistry started in 1895 with William Rutger, who discovers the X-rays. In 1898, we really started studying nuclear chemistry, and that was with Marie and Pierre Curie, who discovered the radioactive elements polonium and radium. But at that point in time, we didn't really know the dangers of nuclear materials. And in 1934, Marie Curie dies of radiation poisoning. In 1945, the Manhattan Project invents the atom bomb, and it was first used in that same year when the atom bomb was dropped on Hiroshima during World War II. So we really got to see the devastating power of nuclear energy. But we also realized that we could use that energy for our benefit in nuclear power plants. In 1986, we had the first big nuclear power plant explosion, which was Chernobyl, and it caused massive environmental damage and casualties. So not only do we see the benefits of nuclear power, but we also see the dangers of nuclear power. Now, some vocab words that we need to know in order to talk about nuclear chemistry efficiently. First, we have radioactive. When something is radioactive, it means that the substance spontaneously emits radiation. And radiation are the rays and particles that are released by radioactive materials. Now, if you're not familiar with the word spontaneous just means that it occurs on its own without any outside energy. Some of the elements on the periodic table are radioactive, and most of them are going to be in that transition metal family. So if we look at the periodic table, we'll see that most of the elements that are radioactive are in the bottom two rows, so row 6 and row 7 of the periodic table. And that's because the bigger the atom is, the less stable its nucleus. So the more likely it is to be radioactive. A nuclear reaction is a reaction that involves a change in the atom's nucleus. So we're familiar with chemical reactions, which is where atoms come together in different combinations in order to form a new compound. In a nuclear reaction, the actual atom itself is going to change. So something in the nucleus is changing in order for it to be nuclear. Nuclear fusion is when two or more lighter atoms combine into a larger one. This is how the heaviest elements are created. Nuclear fission is when there's a splitting of a large atom and the splitting forms lighter elements. The differences between nuclear fusion versus nuclear fission are nuclear fusion combines, nuclear fission splits. Fusion can be found in nature in stars, so like the sun. Fission has only ever been found once in nature, and that was in the ground in Africa. Fusion does not make radioactive particles. Fission does make radioactive particles. In order for nuclear fusion to occur, there needs to be high density and high temperature. That's why it occurs in stars. Fission just needs critical mass and a high-speed neutron. Fusion takes extremely high energy to occur. Fission takes very little energy. Fusion produces more energy than fission reactions, but fission creates more energy than chemical reactions. Fission is what we used when we made the atom bomb. Fusion has not been used yet in wartime, but there is a thing called the hydrogen bomb, and it's even more powerful than the atom bomb. The energy usage of fusion reactions are still experimental. Fission reactions are what we use currently in nuclear power plants. In order to fuel a fusion reaction, hydrogen isotopes are used. And for fission reactions, it's usually uranium. Radioactive decay is when you have an unstable atom and it loses energy by emitting radiation. Atoms are going to go through radioactive decay until they become stable. And stable for an atom, so nuclear stability, is going to be determined by the ratio of neutrons to protons. If the ratio of neutrons to protons is unequal, then the nucleus is not going to be very stable. It's going to need to emit radiation in order to become stable. Atoms that have too many or too few neutrons are going to be unstable. And if we look at this chart, we can see that there is a line of stability. And the line of stability curves at one point, meaning that those bigger elements are going to need more neutrons in order to be stable. That's why the elements towards the bottom of the periodic table, which have equal number of protons and neutrons, are not going to be very stable. They don't have the amount of neutrons that they need to reach that line of stability. Half-life is the time required for half the radioactive isotope to decay. How long the half-life determines what the radioisotope can be used for. So for example, here we have a chart of the half-life of CO60 as it decays. Notice that per half-life, so after one half-life, it's half the amount of grams that it used to have. So at 0 half-life, there's 10 grams. At 1 half-life, there's 5 grams. At 2 half-life, there's 2.5 grams. So it's half of the grams it used to be, not of the original mass. Here we see a couple radioisotopes. Carbon-14 has the shortest half-life of 5,730 years, and uranium-235 has the longest half-life of 704 million years. So the half-lives of certain radioisotopes can vary greatly depending on the radioisotope you're talking about. There is a formula to calculate half-life, which is shown right here, and that is A equals A initial times half to the power of T divided by half-life. So you can use this equation to figure out how much of the radioisotope you'll have left over after a certain amount of time has passed. A nuclear equation shows the atomic number and mass number of the particles involved. In a nuclear equation, we use isotope notation to see how an atom has changed after a radioactive decay has occurred. Remember that isotope notation means that the mass number, which is proton plus neutron, is on top, and the atomic number, which is only protons, is at the bottom. There are 3 types of nuclear reactions. You have alpha decay, beta decay, and gamma decay. Alpha decay is made up of alpha particles. An alpha particle is a helium atom with a mass number of 4, meaning it has 2 protons and 2 neutrons, and an atomic number of 2. An alpha particle has no electrons, meaning that it has a +2 charge, and it's attracted the things that are negatively charged. The alpha particle is going to be your weakest type of radioactive decay. It's so weak that it can't even go through paper. An example of an alpha decay equation is shown here at the bottom. We have Ra222, and on the right side, we see that it emits an alpha particle, so the He, and it decays into Rn218. Beta decay is made up of beta particles. Beta particles are shown by an E with 0 mass and a -1 charge, meaning that they are attracted to things that are positively charged. Beta particles are able to penetrate paper, but they're not able to go through plastic, glass, or aluminum. An example of a beta decay equation is shown at the bottom. We have C14 on the left, and on the right, a beta particle is released, so we have that electron with the -1 charge, and it decays into nitrogen 14. Gamma decays are high energy radiation with no mass, so no protons, neutrons, or electrons, it's just energy, so it has a neutral charge. Gamma rays can penetrate through most anything. They can even go through lead and concrete as long as the layer of lead or concrete is not too thick. When you have an unstable nucleus, it's going to release a gamma ray in order to become more stable. So it's going to release that energy to stabilize its nucleus. An example of a gamma decay equation is shown at the bottom. So on the left, we have He3, which is unstable. So it releases a gamma ray on the right, but notice that even though it released that gamma ray, it's still He3. So the actual subatomic particles in the nucleus did not change. So again, quick overview. Alpha decay has an alpha particle, which is 42He. Beta decays release beta particles, which is 0, -1, E, or it can also be shown by capital B. Gamma decay is 0, 0, and it's that cursive looking Y. So 0, 0, Y. In an alpha decay, the change in atomic mass is a decrease of 4, atomic number decreases by 2. In a beta decay, the mass is unchanged, but the atomic number is increased by 1. And in a gamma decay, the mass and the atomic number are both left unchanged. There are some real-world applications which you can research more about. There's plenty of videos on YouTube, as well as reading material available on the internet. So some real-world applications for nuclear power are nuclear waste. So waste is produced by nuclear power plants. Nuclear waste is hazardous for a really long time, but nuclear power plants don't really create a lot of it. Nuclear energy is used in nuclear power plants, which again are fission reactions in order to produce electricity. And it's way more efficient than fossil fuels. Nuclear medicine, so in small amounts, radioactive materials can be used to look at organ function and structures in the form of X-rays, which again is where the study of nuclear chemistry really started. All right, that is everything you need to know about nuclear chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If this video was helpful, make sure you hit that like button and subscribe so you don't miss any of my future chemistry content. If you would like access to this PowerPoint, it is on my TPT store called Chemistry Made Simple, as well as labs, worksheets, and activities that align with this unit and all other units of high school chemistry. I hope you have a great day. Bye.